The universe is far from silent. Hidden within the vast emptiness are strange signals, a secret language of cosmic messages waiting to be decoded. This journey will reveal how we are learning to understand these whispers from the void. You will gain a completely new way of looking at the night sky, seeing it not as a collection of distant lights, but as an active, speaking universe. We will investigate the sudden, powerful bursts that baffle scientists and ask if a single, famous signal from the past was a message we failed to answer. What do you believe the stars are trying to tell us? Think of the cosmos as a grand orchestra, perpetually performing a symphony of energy. Every star, every galaxy, every spinning neutron star contributes its own unique note to this immense composition. These are the cosmic signals, a language not of words, but of pure physics. They arrive as faint whispers of radio waves, as the brilliant, explosive flashes of gamma-ray bursts, as the subtle ripples of gravitational waves stretching the fabric of space-time itself, and even as ghostly particles called neutrinos that pass through our planet almost unnoticed. This is not random static. It is a structured broadcast carrying profound information. A single, fleeting burst of gamma rays can tell the story of a star's catastrophic death billions of years ago. A persistent, repeating pulse of radio waves might map the furious spin of a dense stellar corpse. The faintest ripple in space-time can narrate the epic, silent dance of two black holes merging into one. To listen to this symphony, we have built extraordinary instruments. Vast radio telescope arrays act as giant ears, scanning the heavens for their faint whispers. Orbiting observatories capture the high-energy light our atmosphere blocks, and incredibly sensitive laser interferometers, with arms kilometers long, feel the infinitesimal stretching of space-time. The raw data they collect is just noise until we apply the rules of physics, the universe's own grammar, to translate it. We decode the intensity, the frequency, and the timing of these signals to understand their cosmic source. What we are really doing is learning to read the universe's diary, written in the language of energy and matter. The deeper we learn this language, the more we can ask the biggest questions. What do these signals tell us about the very first moments of creation? Could one of them be a deliberate message, a single note in the symphony played not by nature, but by another mind? On a quiet August night in 1977, a radio telescope in Ohio captured something extraordinary, a signal so powerful and so unusual that the astronomer who discovered the printed data simply wrote one word in the margin. Wow! This event, lasting a mere 72 seconds, became one of the most famous mysteries in astronomy. It was a strong, narrowband radio wave, precisely the kind of signal theorists predicted an advanced civilization might produce. For decades, the wow signal has fueled our imagination, a tantalizing possibility that we were not alone in the cosmos, if only for a moment. Yet the vast majority of cosmic radio waves have far more natural, though no less spectacular, origins. These are the long-distance messengers of the universe, traveling for millions or even billions of years to reach us. They carry encoded stories from the most energetic objects in existence. We hear the rhythmic, lighthouse-like pulses from spinning neutron stars known as pulsars. We detect the faint whispers from the supermassive black holes at the hearts of distant galaxies called quasars. Each signal is a piece of a puzzle. Scientists like Dr. Jill Tarter, a pioneer in the search for extraterrestrial intelligence, have long argued that radio astronomy is our most promising tool for listening for others. By meticulously analyzing a signal's properties, its exact frequency, its polarization, and any potential modulation, researchers can learn to read this cosmic language. The steady, predictable beat of a pulsar, for instance, is a natural marvel. Decoding its pulses reveals the incredible speed of the star's rotation and the immense strength of its magnetic field. But this process of analysis always leads to a deeper, more profound question. How would a deliberate message crafted by an intelligent mind be different? Would it be complex, structured in a way that nature alone could not achieve? The search continues not just for signals, but for signals that break the natural rules, carrying the unmistakable signature of intention. While the WOW signal remains a singular enigma, the cosmos has since revealed an even more persistent and bewildering phenomenon. Fast radio bursts are the universe's most dramatic short circuits. These are not gentle whispers but colossal, millisecond-long screams of radio energy, each one packing the power of 500 million suns into a flash shorter than a snap of your fingers. Since their initial discovery in data archives, these bursts have arrived from galaxies billions of light-years away, each one a brief, brilliant flare against the dark canvas of space. Their origins are one of modern astronomy's greatest puzzles. The leading suspects are magnetars, which are neutron stars with unimaginably powerful magnetic fields. A starquake on such an object could theoretically unleash a firestorm of radio waves. Other theories point to the catastrophic collisions of neutron stars or the formation of black holes. Dr. Duncan Lorimer, who co-discovered the first of these bursts, sees them as more than just cosmic explosions. He highlights their potential as unique probes. As a fast radio burst travels across the vast intergalactic distances, its journey leaves a fingerprint. The burst's different frequencies get slightly spread out, an effect called dispersion. By measuring this dispersion, scientists can essentially weigh the invisible fog of electrons and matter the signal passed through, allowing them to map the unseen structure of the universe. The mystery deepens with the repeaters. Unlike one-off bursts, some sources, like the famous FRB 121102, flash again and again. This repetition rules out some of the most violent, destructive events, as you cannot have multiple collisions from the same object. It forces astronomers to consider engines that can produce these titanic energies repeatedly, like a highly magnetized star going through periodic, violent convulsions. The very nature of these repeating signals, their precise and complex structures, inevitably leads to a tantalizing, almost heretical thought. Are we witnessing a natural, if spectacular, cosmic process? Or could the consistent, patterned nature of some bursts hint at a source that is, in some way, guided? Exploring fast radio bursts does more than just catalog cosmic violence. It opens a direct window into the most extreme physics, where the laws of nature are pushed to their absolute limits. While fast radio bursts scream across the cosmos, another, far more subtle language is being spoken. It is written not in light or radio waves, but in the very fabric of reality itself. Gravitational waves are ripples in spacetime, faint tremors sent out by the most violent events in the universe. Picture the cosmos as a still, silent pond. When a massive cosmic event occurs, like two black holes colliding, it is like a stone being dropped into that water. The impact sends ripples expanding outward at the speed of light, subtly stretching and squeezing everything in their path, including the space we occupy. For a century, this was just a beautiful prediction from Einstein's theory of relativity. Then, in 2015, the LIGO Observatory made the first direct detection. The source was two black holes, each over 30 times the mass of our Sun, spinning around each other and finally merging into one. The signal they detected was the chirp, the final frantic ripples of that cosmic collision. As the renowned physicist Dr. Kip Thorne has often explained, this was not just a confirmation of a theory. It opened an entirely new sense with which to perceive the universe. We are no longer just looking at the cosmos. We are now listening to its vibrations. Each gravitational wave signal carries an encoded story. By analyzing the precise shape of the wave, the way its frequency and amplitude change over time, scientists can perform a kind of cosmic forensics. They can deduce the masses of the objects that collided, how fast they were spinning, and even how far away the cataclysm occurred. This new sense revealed its full power in 2017 with the detection of a different kind of merger. This time it was two neutron stars, the incredibly dense corpses of dead stars. The gravitational wave signal was accompanied by a flash of gamma rays and a burst of light across the entire electromagnetic spectrum. This event marked the dawn of multi-messenger astronomy. For the first time, we could both hear the ripples in spacetime and see the brilliant fireworks show it produced. It was like listening to a symphony while also watching the conductor, a complete sensory experience of a cosmic event. This multifaceted approach is the future of decoding the universe's secrets. Gravitational waves could one day reveal the nature of dark matter or carry echoes from the very first moments after the Big Bang, a time forever hidden from traditional telescopes. What other silent, world-shaking events are sending their faint tremors through the void, waiting for our instruments to become sensitive enough to hear them? Gravitational waves ripple through space-time, but another messenger slips through the cosmos completely unseen. Neutrinos are ghostly particles, so ethereal that trillions pass through your body every second without a single interaction. They are the universe's perfect couriers, born in the hearts of its most violent events and traveling outward, unaffected by magnetic fields or clouds of dust that would block or bend light. This ghostly nature makes them our only direct window into the deepest, most hidden cosmic engines. When a massive star explodes as a supernova, the cataclysm begins deep within its core. The light from this explosion takes hours to fight its way to the surface and burst into view, but neutrinos, born in the nuclear fire of the collapsing core, escape almost instantly. They race ahead of the light, carrying the news of the star's death across space. If our detectors are sensitive enough, a sudden pulse of neutrinos can provide an early warning, telling astronomers exactly where and when to point their telescopes to watch the fireworks begin. To catch these phantoms, we have built some of the strangest observatories on Earth. The Ice Cube Neutrino Observatory is a colossal instrument buried deep in the Antarctic ice. It uses a cubic kilometer of pristine ice as a detection medium, waiting for the incredibly rare moment a neutrino finally interacts with an atom. When it does, it produces a faint flash of blue light, which is captured by thousands of sensitive optical sensors. For decades, these detectors saw neutrinos from the Sun and our own atmosphere, but the sources of the highest energy neutrinos remained a mystery. That changed in 2018. A high-energy neutrino was detected by IceCube, and its path was traced back across the cosmos to a blazar known as TXS 0506 plus 056. A blazar is a galaxy centered on a supermassive black hole that is firing a jet of radiation directly at Earth. This single detection was a monumental breakthrough. For the first time, we had identified a specific object outside our galaxy as a cosmic accelerator, a natural particle collider of unimaginable power. Nobel laureate Dr. Arthur B. MacDonald has emphasized how neutrinos reveal processes completely hidden from traditional telescopes. They show us the furious particle acceleration happening within those jets, a process we could never see with light alone. So how do these silent messengers complete the cosmic picture? While gravitational waves tell us about massive objects moving, and light and radio waves show us the hot, energetic aftermath, neutrinos take us directly to the engine room. They are the only signal that comes straight from the particle acceleration itself, pointing an unwavering finger back to their source. They are the final, crucial piece of evidence in a multi-messenger investigation, confirming our theories about where the universe's most powerful energies are born. These ghostly neutrinos point back to cosmic engines, but some of those engines produce explosions so violent they redefine the word power. Gamma-ray bursts are the universe's ultimate fireworks, sudden blasts of gamma-ray light so intense they can outshine 1,000,000 trillion suns. For a few fleeting seconds, a single one of these events releases more energy than our sun will over its entire 10-billion-year lifetime. This energy travels across billions of light years, a beacon from the most catastrophic births and deaths in the cosmos. The trigger for a long gamma-ray burst is a star's final dramatic act. Imagine a massive star much heavier than our sun, exhausting its nuclear fuel. Its core can no longer support its own immense weight, and it collapses in on itself in a fraction of a second. This collapse forges a newborn black hole. From the chaos around this new singularity, twin jets of matter and radiation erupt at nearly the speed of light. If one of those jets is pointed directly at Earth, we see it as a brilliant, long-duration gamma-ray burst, often followed by the fading light of the star's supernova explosion. Shorter bursts lasting less than 2 seconds tell a different, equally violent story. These are the echoes of a different kind of merger, the final, deadly spiral of two ultra-dense neutron stars or a neutron star and a black hole. As these objects collide, they also create a black hole and launch similar jets of energy, resulting in a brief, incredibly bright flash. The late Dr. Neil Gehrels, a visionary in this field, led the development of NASA's Swift satellite, a remarkable observatory designed to catch these flashes as they happen. Swift automatically swivels to observe the burst's afterglow, the fading ember of the explosion that radiates in X-rays, ultraviolet, and visible light. This afterglow is the key to unlocking the burst's secrets. By analyzing this light, astronomers can determine the burst's immense distance and pinpoint the galaxy it came from. One of the most significant bursts ever recorded, known as GRB 130427A, was detected in April 2013. It was astonishingly bright and relatively close, cosmically speaking. This single event provided a treasure trove of data, allowing scientists to study the detailed physics of the jet and the phenomenal particle acceleration within it. The data confirmed that these bursts are natural particle accelerators on a scale we could never hope to build on Earth. But these explosions do more than just destroy. They might also be crucial creators. The titanic conditions within a gamma-ray burst, and especially in the neutron star mergers that cause the short ones, are believed to be cosmic forges. It is in these extreme environments that atoms are smashed together to form the heaviest elements in the universe, like gold, platinum, and uranium. A single merger might forge an amount of gold equal to the mass of our entire planet, scattering these precious metals into space to one day become part of new stars, planets, and perhaps even life. So when we detect a gamma-ray burst, we are witnessing a fundamental engine of cosmic change. These flashes are not just random violence. They are the birth cries of black holes, the creators of the elements that make up our world, and probes that illuminate the distant, early universe. They force us to ask what other cosmic secrets are hidden within these brief, universe-shaking blasts of light. Carl Jansky was simply trying to identify the source of static disrupting transatlantic radio calls in the 1930s. His rotating antenna, nicknamed Jansky's merry-go-round, picked up a persistent hiss that slowly moved across the sky each day. He had not found an earthly source of interference. He had discovered the center of our own Milky Way galaxy, broadcasting in radio waves. The cosmos had spoken, and for the first time we had an instrument capable of hearing it. This faint static was not noise. It was a story, the collective voice of countless stars and cosmic processes, waiting to be understood. An amateur astronomer and radio engineer named Grote Reber was captivated by this discovery. In his own backyard, he built the first dedicated radio telescope, a parabolic dish nearly 10 meters across. For years, he was the only person in the world doing radio astronomy, patiently scanning the heavens and publishing the first rough maps of the radio sky. He proved that Jansky's finding was not a fluke. The universe was filled with this invisible light, a silent symphony we had been deaf to for all of human history. The true potential of this new sense revealed itself dramatically in 1967. A graduate student named Jocelyn Bell Burnell was reviewing data from a radio telescope she had helped build when she noticed a peculiar, repeating signal. It was a series of pulses so precise and regular that they seemed artificial. The source was jokingly labeled LGM1 for little green men. The truth, when it was finally uncovered, was almost as strange. They had discovered the first pulsar, a rapidly spinning neutron star sweeping the universe with a lighthouse beam of radiation. This moment was a profound lesson. The most mysterious, seemingly intelligent signal had a breathtaking natural explanation, revealing a new type of object whose existence was only possible under the most extreme laws of physics. Our tools grew alongside our ambition. The colossal Arecibo dish, nestled in a natural karst sinkhole in Puerto Rico, became an icon of human curiosity for decades, its giant ear listening for faint whispers from distant pulsars and just maybe for voices other than our own. In space, the Hubble telescope showed us that to decode the cosmos, we needed to see it in all its forms of light, free from the distortion of our atmosphere. Each technological leap brought a new revelation. The faint, uniform static of the cosmic microwave background radiation, detected by accident, was finally recognized as the cooled remnant of the Big Bang itself, the oldest signal in the universe. This historical journey from misidentified static to the discovery of the universe's birth cry has fundamentally shaped how we listen today. It taught us patience. It taught us that nature is often more inventive than our wildest speculations, and it taught us to build not just one kind of ear, but an entire orchestra of instruments, each tuned to a different part of the cosmic symphony. This hard-won foundation is what now allows us to pursue the universe's deepest secrets, not as passive listeners, but as active decoders of a story that began billions of years ago. This deliberate search for a cosmic companion defines the work of the SETI Institute. The search for extraterrestrial intelligence is humanity's most focused effort to find a signal that was meant to be found. It is the difference between listening to the ocean's natural roar and straining to hear a single, deliberate voice calling out across the water. Imagine a global network of radio telescopes, their immense dishes pointed at distant stars, sifting through the endless cosmic static. They are not listening for the natural rhythms of pulsars or the explosive bursts from dying stars. They are searching for a pattern that breaks the rules, a signal that nature alone could not have created. This could be a narrowband radio transmission, a laser pulse blinking in a complex code, or even the shadow of an immense structure built around a star by a civilization harnessing its entire energy output. These potential signs of advanced technology, called technosignatures, are the ultimate prize. The quest was pioneered by visionaries like Frank Drake, who conducted the first modern SETI experiment, Project Ozma, in 1960. His famous equation, a way of estimating the number of communicative civilizations in our galaxy, framed the scientific possibility of the search. Today, projects like the Allen Telescope Array, a sprawling collection of dishes in Northern California, automate this listening. They monitor millions of radio frequency channels simultaneously, a vast and patient electronic ear. Yet for all our listening, the cosmos remains silent in a way that begs a profound question. This is the Fermi Paradox, a concept often discussed by senior astronomer Dr. Seth Shostak. If the universe is so vast and so old, with billions of planets that could support life, then where is everybody? Why have we not found any evidence? The paradox forces us to consider sobering possibilities. Perhaps intelligent life is exceedingly rare, or maybe it arises frequently but tends to destroy itself before it can master interstellar travel or communication. It is possible we are simply not listening correctly, or that their chosen methods of signaling are beyond our current technology to comprehend. This search is punctuated by moments of thrilling ambiguity. The famous WOW signal from 1977 remains the classic example, a powerful, unexplained burst that has never been repeated. More recently, a signal designated BLC-1 appeared to originate from the direction of our closest stellar neighbor, Proxima Centauri. It was a narrowband signal that seemed promising, but after intense analysis, it was ultimately attributed to human-made radio interference. These events highlight the immense challenge of the search, separating the faint whisper of a potential message from the overwhelming roar of our own technological noise. They force us to confront a critical question. What would we actually do if a signal was confirmed? There are official, though non-binding, protocols in place. They call for international verification, a careful analysis to understand the message's content, and a global discussion before any response is considered. This quest is far more than a technical endeavor. It is a scientific pursuit that brushes directly against the deepest philosophical questions we can ask. Are we a cosmic accident, a solitary spark of consciousness in a vast, unconscious void? Or are we one voice in a grand, galactic chorus, simply waiting for the right frequency to finally join the conversation? A prime number sequence beaming from the stars would stop every astronomer on the planet. Its stark, mathematical purity would stand in complete defiance of the messy, energy-driven signals we typically observe. This is the critical frontier in our cosmic decoding effort, the fine line between a natural phenomenon and a potential message. Nature operates on the laws of physics, which produce signals with a certain kind of order. A pulsar's pulse is a perfect metronome governed by the star's steady rotation. The chirp of merging black holes follows the precise, predictable equations of general relativity. These signals have high energy, but they are low in what experts like Dr. Paul Davies would call information content. They tell us what happened, but they do not convey a complex message. An artificial signal, one crafted by an intelligence, would likely be different. It might be inefficient from an energy perspective, filled with redundancy or complex patterns that serve no obvious physical purpose. It could use a framework based on universal concepts, like mathematics or the fundamental constants of physics. A sequence of prime numbers is the classic example because primes are not a product of any known physical process. They are a purely mathematical construct, a universal language any technological civilization would likely recognize. The challenge is that nature is endlessly creative and sometimes deceiving. The repeating patterns of some fast radio bursts initially sparked excitement because repetition feels intentional. Yet further analysis, studying their dispersion and polarization, has consistently pointed back to powerful astrophysical engines like magnetars. The universe can produce astonishingly complex rhythms without any guiding mind. To sift through the colossal noise of the cosmos, we are now turning to advanced machine learning algorithms. These systems can analyze terabytes of telescope data, learning the subtle fingerprints of known natural phenomena. Their true value lies in spotting the outlier, the signal that does not fit any known profile, the one that breaks all the established rules. This moves us beyond human bias, allowing us to search for patterns we might not even think to look for. This entire effort forces us to confront a deep-seated limitation, our own anthropocentrism. We are inherently biased to look for signals we would send, to imagine messages based on our own logic and technology. A truly advanced intelligence might communicate in a way we cannot yet conceive, using quantum entanglement or manipulating spacetime itself. Their message might not be a simple hello, but a complex data stream containing a library of knowledge, or a set of engineering instructions we lack the context to understand. The analytical framework we build must be flexible enough to recognize intelligence not by its resemblance to our own, but by its fundamental signature of design. It must separate the symphony of the cosmos from the single, deliberate note played by another composer. This rigorous approach ensures our search remains a science, not just a flight of fancy, as we listen for a voice that is not just strange but truly other. A prime number sequence beaming from the stars would stop every astronomer on the planet. Its stark, mathematical purity would stand in complete defiance of the messy, energy-driven signals we typically observe. This is the critical frontier in our cosmic decoding effort, the fine line between a natural phenomenon and a potential message. Nature operates on the laws of physics, which produce signals with a certain kind of order. A pulsar's pulse is a perfect metronome governed by the star's steady rotation. The chirp of merging black holes follows the precise, predictable equations of general relativity. These signals have high energy, but they are low in what experts like Dr. Paul Davies would call information content. They tell us what happened, but they do not convey a complex message. An artificial signal, one crafted by an intelligence, would likely be different. It might be inefficient from an energy perspective, filled with redundancy or complex patterns that serve no obvious physical purpose. It could use a framework based on universal concepts, like mathematics or the fundamental constants of physics. A sequence of prime numbers is the classic example because primes are not a product of any known physical process. They are a purely mathematical construct, a universal language any technological civilization would likely recognize. The challenge is that nature is endlessly creative and sometimes deceiving. The repeating patterns of some fast radio bursts initially sparked excitement because repetition feels intentional. Yet further analysis, studying their dispersion and polarization, has consistently pointed back to powerful astrophysical engines like magnetars. The universe can produce astonishingly complex rhythms without any guiding mind. To sift through the colossal noise of the cosmos, we are now turning to advanced machine learning algorithms. These systems can analyze terabytes of telescope data, learning the subtle fingerprints of known natural phenomena. Their true value lies in spotting the outlier, the signal that does not fit any known profile, the one that breaks all the established rules. This moves us beyond human bias, allowing us to search for patterns we might not even think to look for. This entire effort forces us to confront a deep-seated limitation, our own anthropocentrism. We are inherently biased to look for signals we would send, to imagine messages based on our own logic and technology. A truly advanced intelligence might communicate in a way we cannot yet conceive, using quantum entanglement or manipulating spacetime itself. Their message might not be a simple hello, but a complex data stream containing a library of knowledge or a set of engineering instructions we lack the context to understand. The analytical framework we build must be flexible enough to recognize intelligence not by its resemblance to our own, but by its fundamental signature of design. It must separate the symphony of the cosmos from the single, deliberate note played by another composer. This rigorous approach ensures our search remains a science, not just a flight of fancy, as we listen for a voice that is not just strange but truly other. Deciphering a message from the stars would be the ultimate translation challenge. We are not just dealing with a foreign language, but a language developed in an entirely different world, by minds that may perceive reality in ways we cannot fathom. This is the domain of Xenolinguistics, a field that applies the principles of linguistics to the hypothetical task of decoding an interstellar message. The core challenge is a profound lack of shared context. Think of the Rosetta Stone, which provided the same text in 3 known scripts, allowing for cross-referencing. An alien message would offer no such anchor. There would be no shared dictionary, no familiar cultural references, not even a guarantee that their basic sensory experiences like sight or sound resemble our own. Researchers like Dr. Sherry Wells Jensen explore how we might bridge this unimaginable gap. She and others suggest that the only truly universal common ground might be the laws of physics and mathematics. A message might begin by establishing fundamental concepts like the number 1, the structure of a hydrogen atom, or the ratios of prime numbers. These are constants that any technological civilization would inevitably discover. Our own attempts at sending messages have relied on this very idea. The pioneer plaques attached to spacecraft now drifting between the stars used diagrams of hydrogen energy states and a map of our solar system to indicate our location and scientific understanding. The Voyager Golden Records went further, encoding images, sounds, and music from Earth, assuming that a species capable of interstellar travel could decode the instructions and perceive the symbols we consider universal. But this approach is fraught with risk. A simple image of a hand in a greeting could be interpreted as a threat, or a diagram of our solar system might be completely misunderstood without a shared sense of scale or perspective. The danger of misinterpreting metaphor, intention, or even basic declarative statements is immense. How would we distinguish a friendly hello from a warning, or a philosophical treatise from a technical manual? To tackle this, scientists are now training advanced machine learning models to search for complex, grammar-like structures within signal data. These algorithms are not looking for meaning, but for pattern. They can analyze a string of symbols or a modulated signal for signs of syntax, the rules that govern how elements are ordered, and for evidence of recursion, the embedding of structures within other structures, which is a hallmark of human language. A signal exhibiting these properties would be a powerful candidate for an artificial message, even if its content remained a complete mystery. This linguistic perspective forces a humbling realization. Decoding a message is not a purely technical problem to be solved with a bigger computer. It is a deeply cultural and philosophical endeavor. It requires us to step outside our own cognitive framework and imagine a mind that communicates without words, that thinks in concepts we have no names for. The true message we receive might not be in the content, but in the structure itself, revealing a mode of thought utterly alien to our own. What profound truths about the universe or about the nature of consciousness itself might be locked within a grammar we have yet to understand? On a computer printout, a single string of letters and numbers was circled in red pen. Next to it, one word was written in all capital letters: "Wow." This was the moment astronomer Jerry Amon first laid eyes on a signal so extraordinary it would haunt the field of cosmic listening for decades. The data came from the Big Ear radio telescope at Ohio State University on August 15, 1977. For 72 seconds, the telescope recorded a signal that was both powerful and precisely tuned. It was a narrowband radio transmission concentrated on one specific frequency, just as scientists predicted an artificial, interstellar message would be. It rose and fell in intensity exactly as a signal from a fixed point in space would, as the Earth's rotation carried the telescope's beam across it. Then it vanished, never to be heard again. The signal appeared to originate from the direction of the constellation Sagittarius, a crowded region of the Milky Way. Its unique signature made it a perfect candidate for the one thing everyone was hoping to find: a message. Yet, its fleeting nature is the very source of its enduring mystery. How can you verify a signal that never repeats? Astronomers have pointed their dishes toward that same patch of sky countless times over the years, listening for another whisper, another hint. The silence has been absolute. Dr. Amon himself spent years considering every possible natural explanation. One theory suggested the signal might have been a reflection off a piece of space debris. Another proposed it was emissions from a passing comet, but the specific comets suggested were not in the right part of the sky at that time. None of the natural hypotheses have managed to fully account for the signal's unique combination of strength, frequency, and behavior. The WOW signal is the ultimate ghost story of astronomy, a single, brilliant flash of something that defies easy categorization. It stands as a powerful lesson in the challenges of studying transient cosmic phenomena. The universe is under no obligation to repeat its mysteries for our convenience. A one-time event, no matter how compelling, remains just that, an event. It cannot be tested, cannot be analyzed with modern tools, and cannot be confirmed. This single, enigmatic event forces us to confront the limitations of our search. It underscores the absolute necessity for persistent, patient monitoring of the skies, and for a technological infrastructure that can capture and analyze such fleeting events in real time, from multiple locations across the globe. The WOW signal is a monument to what might have been, a question mark written in the stars that continues to ask us, what are we truly prepared to hear? The universe's metronome ticks with astonishing precision. Pulsars are the rapidly spinning cores of dead stars, celestial lighthouses sweeping beams of radiation across the cosmos with a regularity that rivals the most accurate atomic clocks on Earth. When that beam flashes across our line of sight, we see a pulse. The discovery of this phenomenon in 1967 by Jocelyn Bell Burnell was a moment of profound bewilderment. The signal was so unnervingly regular, so artificial in its rhythm, that her team half-seriously considered the possibility of little green men. They had stumbled upon a new kind of natural object so extreme it mimicked the signature of intelligence. This initial confusion reveals a deep truth about the cosmos. Nature, under the most intense physical conditions, can produce patterns that appear deliberately crafted. The power of a pulsar lies in this very predictability. Each pulse is a coded message from the star itself. By measuring the subtle changes in the timing of these pulses, astronomers can perform a kind of cosmic diagnosis. They can deduce the pulsar's mass, the incredible strength of its magnetic field, and even feel the faint tugs of orbiting planets. In fact, the very first planets ever discovered outside our solar system were found not around a sun-like star, but orbiting the pulsar PSRB 1257+12. Its rhythmic pulses were slightly disturbed by the gravitational pull of its unseen worlds, revealing a completely new planetary system born from the ashes of a stellar explosion. This makes pulsars more than just curiosities. They are tools. Their steady beats allow scientists to test Einstein's theory of general relativity with incredible precision, observing how their signals are warped by gravity. They act as probes to map the invisible fog of gas and dust between the stars, as their signals slow down slightly when traveling through this interstellar medium. And their flawless timing has inspired concepts for a galactic positioning system, where future spacecraft could navigate the void between stars by locking onto the coordinated pulses of these distant beacons. The most ambitious use of these natural clocks is the creation of a pulsar timing array. By monitoring a network of millisecond pulsars scattered across the galaxy, scientists are attempting to detect the faint, constant hum of low-frequency gravitational waves. These are not the chirps from individual black hole mergers, but the steady background rumble from countless collisions over cosmic time, a symphony of spacetime vibrations that could reveal the universe's largest-scale dynamics. What other fundamental forces, hidden in plain sight, might we uncover by listening to the universe's most reliable timekeepers? Frank Drake's equation is a mathematical vessel for our deepest cosmic curiosity. It is not a promise of contact, but a structured way to organize our ignorance and our hopes. He framed the question in 1961, before we had confirmed a single planet outside our own solar system. His formula is a chain of probabilities, a series of terms multiplied together. It begins with the number of new stars born each year in our galaxy. Then it asks what fraction of those stars have planets. Of those planets, how many are in the habitable zone where liquid water could exist? The equation then ventures into biology, considering on how many of those suitable worlds life actually emerges. Next, it asks how often that life evolves into intelligent, tool-using beings. And finally, the most haunting variable of all, the average lifespan of a communicative civilization. How long does a technological society last before it succumbs to self-destruction or simply falls silent? For decades, most of these terms were little more than educated guesses. We could estimate the first few factors, but the later ones were a complete mystery, leaving the final number anywhere from one, just us, to millions. The discovery of exoplanets has been a revolution for this equation. We now know that planets are not rare exceptions, but the common outcome of star formation. Telescopes like Kepler have revealed a staggering diversity of worlds, with billions of sun-like stars in our galaxy alone likely hosting rocky planets in their habitable zones. This has transformed the early terms of the equation from speculation into solid data. Scientists like Dr. Sarah Seeger are now pushing the next frontier, searching for biosignatures, specific combinations of gases in a planet's atmosphere, like oxygen and methane, that could only be sustained by living processes. The hunt is also on for technosignatures, the signs of advanced technology, such as city lights on the night side of a world, or industrial pollutants in its atmosphere. Each new discovery tightens the constraints on Drake's famous formula, yet the final variables remain profoundly uncertain. Is the emergence of intelligence an inevitable outcome of evolution, or a cosmic fluke? And what is the typical lifetime of a technological species? This is where the equation becomes a mirror. Our assumptions about these final terms say more about our own fears and aspirations for humanity's future than they do about alien civilizations. If technological species commonly destroy themselves within a few centuries of discovering radio, then the galaxy might be filled with the silent ruins of civilizations that blinked out long ago. This probabilistic framework directly shapes the search for signals. If the galaxy is teeming with life, then a targeted, patient search makes sense. If we are among the very first or the very last, then the effort becomes far more daunting. The James Webb Space Telescope is now providing unprecedented data on the atmospheres of distant worlds, offering the first real chance to detect potential biosignatures. Each new piece of data feeds back into the equation, refining our estimates and guiding our listening strategies. The Drake equation endures not because it gives us answers, but because it so perfectly articulates the questions. It forces us to weigh the staggering scale of the cosmos against the fragile nature of a technological candle flame. How many of those flames are burning right now, and how many have already been extinguished by the dark? The silence of the cosmos is not an empty void, but a profound statement. Enrico Fermi's famous question, "Where is everybody?" cuts to the heart of our cosmic loneliness. We gaze at a galaxy filled with billions of potentially habitable worlds, a statistical promise of company, and yet we are met with an unbroken quiet. This is the Fermi Paradox, the staggering contradiction between the high probability of extraterrestrial life and the utter lack of any evidence for it. The universe appears to be a stage set for a grand party, but when we listen at the door, we hear nothing. Proposed solutions to this puzzle force us to confront unsettling possibilities about the nature of life and intelligence itself. One of the most sobering is the Great Filter Hypothesis, developed by thinkers like Dr. Robin Hanson. This idea suggests that somewhere along the evolutionary path from non-life to a spacefaring civilization, there exists a barrier, a step so improbable that almost every potential civilization fails to pass it. This filter could lie in our past. Perhaps the spontaneous emergence of life is the cosmic fluke, and we are truly alone. Or, more ominously, it could lie in our future. Maybe the development of advanced technology inevitably leads to self-destruction through war, environmental collapse, or a technology we have yet to invent. In this scenario, the silence we hear is the echo of countless civilizations that burned brightly for a moment and then flickered out. A less grim but equally humbling idea is the zoo hypothesis. This proposes that advanced civilizations are out there, and they are aware of us, but they have chosen to place us in a kind of cosmic quarantine. They observe us from a distance, allowing our society to develop naturally without interference, following a prime directive of non-contact. Our planet might be a protected wilderness area in a vast galactic park. Other explanations are more technological. Perhaps civilizations do not last long in a communicative phase, quickly advancing beyond the crude technology of radio broadcasts into a realm we cannot perceive. Their conversations might be carried on through quantum networks or gravitational waves, using a channel we are still deaf to. Or maybe the vast distances between stars and the immense timescales of cosmic evolution simply mean that civilizations rise and fall without ever overlapping in a window of time long enough to communicate. The Fermi Paradox fundamentally shapes how we decode the universe. It teaches us that the absence of a signal is data. This great silence pushes us to broaden our search, to look not just for deliberate messages, but for the archaeological traces of those who came before. We must search for Dyson spheres, vast structures built around stars to harness their energy, or for the thermodynamic waste heat of a galaxy-spanning civilization. The paradox is a philosophical mirror, forcing us to ask not only where they are, but what our own future might hold. Are we listening for a hello, or are we listening for an epitaph? The search for a cosmic companion is no longer limited to listening for a deliberate hello. We are now learning to look for the silent, sprawling artifacts a civilization might leave behind. These are technosignatures, the detectable signs of advanced technology that could reveal a society's presence across the galaxy, whether it intends to communicate or not. Imagine a star that flickers in an impossible way. Tabby's star, discovered by citizen scientists, did exactly that, dimming by enormous and irregular amounts. While the most likely explanation is a cloud of dust, its strange behavior sparked serious scientific discussion about the possibility of a Dyson sphere, a hypothetical megastructure built around a star to capture its entire energy output. Such a structure would irradiate the star's light as waste heat, glowing brightly in the infrared part of the spectrum. Astronomers like Dr. Jason Wright champion this broader view. He suggests we use our most powerful infrared telescopes to scan the skies for the telltale warmth of cosmic engines, the thermal signature of a civilization operating on a staggering scale. This search extends to the surfaces of distant worlds. Powerful future telescopes might one day detect the artificial glow of city lights on the night side of an exoplanet, or the specific chemical fingerprints of industrial pollution in its atmosphere. These signs would not be a message but a side effect of a world alive with industry. Even the methods of travel could leave a trail. An interstellar light sail, propelled by powerful lasers, might reflect a brilliant and fleeting flash of light as it journeys between stars, a beacon announcing a ship's passage. Similarly, a civilization might use tightly focused laser pulses for its own communications, creating narrow beams of light far more efficient than radio waves. Our telescopes could detect these as extremely brief, intense flashes, a kind of cosmic Morse code. This expanded paradigm fundamentally shifts the challenge. How do we distinguish the waste heat of a Dyson sphere from the natural glow of a dust-shrouded young star? How do we tell the city lights of a civilization from the brilliant auroras of a world with a powerful magnetic field? The answer lies in context and persistence. A technosignature would likely be persistent, unlike a fleeting radio burst. It would exist in a specific, telling environment, like the habitable zone of a stable star. And its light signature would contain spectral lines that simply do not match any known natural chemical process. We are no longer just listening for a voice in the crowd. We are learning to spot the footprint of an entire civilization, a mark on the cosmos that says, "We were here, we built this." What other indelible marks might an advanced society leave upon the stars, silently waiting for us to notice? 25,000 years from now, a faint coded signal will finally arrive at its destination. In 1974, humanity broke its long silence. Using the powerful Arecibo radio telescope, a team led by Frank Drake and Carl Sagan transmitted a deliberate message into the cosmos, aimed at the M13 star cluster, a dense collection of hundreds of thousands of stars. This was not a passive act of listening, but an active shout into the void, a single sentence in a conversation we had only just begun to hear. The message itself was a masterpiece of scientific compression. It was a string of 1,679 binary bits, ones and zeros, carefully arranged in a rectangular grid of 73 rows by 23 columns. This specific number was chosen because it is the product of two prime numbers, a structural clue meant to signal that this was an intelligent construction, not a natural emission. To decode it, an intelligence would first need to recognize this prime number pattern, then arrange the bits into the correct grid to reveal a pictogram, a picture packed with information about us. The top section laid out the numbers from 1 to 10 in binary, establishing a universal mathematical foundation. Below that, it displayed the atomic numbers for the key elements of life: hydrogen, carbon, nitrogen, oxygen, and phosphorus. Then came a schematic of the DNA double helix, with the number of nucleotides in a human genome written alongside it. A crude graphic of a human figure was included, showing our average height relative to the wavelength of the transmission, and next to it, a diagram of our solar system with Earth offset to indicate its significance. This entire message was a time capsule, a bottle cast into the cosmic ocean. Yet its journey is so long that by the time it reaches the M13 cluster, the stars will have moved, and the civilization that sent it may be unrecognizable to itself. This symbolic act was never about a practical expectation of a reply. It was a declaration of our own existence, a testament to our desire to reach out and connect. But this impulse to announce ourselves is not without its critics. The late Stephen Hawking voiced a profound concern, drawing a stark analogy. He suggested that if an advanced civilization discovered us, the consequences could be similar to when Europeans arrived in the Americas, a scenario that did not end well for the native populations. His warning forces a difficult ethical question. Do we have the right to speak for all of humanity and for all future generations by drawing attention to our world? The Arecibo message exemplifies the ideal of using universal constants as a common language. The structure of DNA, the mathematics of prime numbers, the fundamental elements, these are things we believe any technological civilization would understand. It is our best guess at a cosmic Rosetta Stone, but this very act of reaching out creates a deep responsibility. What if our message is misunderstood? What if our peaceful pictogram is interpreted as a declaration of territory or a threat? The act of sending forces us to grow up as a species, to consider our place in a galactic community that may be far older and far more complex than we can imagine. This outgoing signal is the bold counterpart to our patient listening. It completes the circuit of communication, transforming us from mere eavesdroppers on the cosmic symphony into potential participants. Are we ready to accept the consequences of someone someday finally answering back? Tucked within the faint static of a forgotten antenna lies the oldest story ever told. The cosmic microwave background is the cooled remnant of the universe's fiery birth, a fossilized echo of the Big Bang that still permeates every corner of space. It is a whisper of light from a time when the cosmos was a searing hot plasma, a mere 380,000 years old. Before this moment, the universe was an opaque fog, too dense for light to travel. As it expanded and cooled, atoms finally formed, and the first rays of light were set free, traveling for billions of years to reach us as this faint microwave glow. Arno Penzias and Robert Wilson stumbled upon this signal in 1965, trying to eliminate a persistent, annoying hiss from their radio telescope. They scrubbed away pigeon droppings, checked every connection, but the noise remained. They had not found a technical fault. They were hearing the faint but unmistakable afterglow of creation itself. This discovery transformed cosmology from speculation into a precision science. Later missions like the COBE satellite led by Dr. John Mather made the next critical leap. It revealed that this cosmic background is not perfectly smooth. Its spectrum is that of an almost perfect black body, a thermal snapshot of the young universe, confirming the Big Bang model with stunning accuracy. But the true treasure was in the tiny imperfections, the anisotropies. These minute variations in temperature, mere millionths of a degree, are the universe's genetic blueprint. They are the seeds of all future structure, the slightly denser patches where gravity would eventually pull matter together to form the first stars, galaxies, and everything we see today. The Planck space mission later mapped these fluctuations with exquisite detail, creating a cosmic fingerprint that encodes profound secrets. By decoding this pattern, cosmologists can weigh the invisible components of the cosmos. The specific size and distribution of these hot and cold spots tell us how much dark matter must be present to sculpt the galaxies, and how dark energy is driving the universe's accelerating expansion. This ancient light is our most powerful tool for testing theories of cosmic inflation. that fantastically rapid expansion in the first fraction of a second. The patterns we see are consistent with this violent stretching, which magnified quantum fluctuations into the cosmic structures we observe. As we refine our instruments, what deeper truths might this primordial text reveal? Could future CMB observations uncover the faint imprint of gravitational waves from the instant of inflation, a direct glimpse into the era of quantum gravity? Might they even reveal evidence of a collision with another universe, a cosmic bruise from beyond our own spacetime? The cosmic microwave background is more than a relic. It is the foundational document of reality, a message from the very beginning, and we are only just learning to read its deepest chapters. A different kind of signal might be encoded in the fabric of reality itself, one that operates on the bizarre rules of the quantum world. Quantum entanglement, what Einstein called spooky action at a distance, links two particles so intimately that affecting one instantly influences its partner, no matter how far apart they are. This connection seems to defy the cosmic speed limit of light, suggesting a potential channel for communication that is both instantaneous and profoundly secure. Picture an advanced civilization establishing a quantum network across interstellar space, using entangled particles as the ultimate cipher. Any attempt to eavesdrop on such a transmission would disturb the delicate quantum state, immediately revealing the intrusion and collapsing the message into noise. This is not just a theoretical dream. On Earth, scientists are already building the foundations of this technology. China's MISHA satellite has successfully demonstrated quantum key distribution between ground stations and orbit, creating unbreakable encryption keys by beaming entangled photons across hundreds of miles. While we cannot use this for faster-than-light messaging yet, the principle is proven. Theorists like Dr. Anthony Aguirre suggest that a sufficiently advanced society might have mastered quantum communication on a cosmic scale, using it as their primary, undetectable method for exchanging information. Their conversations would be woven into the quantum vacuum, completely hidden from our conventional radio telescopes. The quantum realm could also leave its fingerprint on the signals we already observe. The hunt for a theory of quantum gravity, which unites the very large with the very small, might find clues in the ripples of spacetime. As gravitational waves travel across the universe, the subtle, foamy texture of spacetime at the quantum scale could subtly alter their waveform. By analyzing these ripples with extreme precision, future observatories might detect these tiny imprints, finding the signature of quantum gravity written into the stories of colliding black holes. This cutting-edge frontier merges the quest for fundamental physics with the art of communication. It forces us to ask a profound question. If an advanced intelligence is speaking, are we simply listening on the wrong channel, deaf to a conversation happening all around us in a language of entanglement and superposition? A silent revolution is unfolding in our search for cosmic meaning, powered by artificial intelligence. Our telescopes now collect more data in a single day than an astronomer of the past might have analyzed in a lifetime. This deluge of information is so vast that human minds alone can no longer sift through it all. We have built the ears to hear the universe, and now we are building the brains to understand what it is saying. Machine learning algorithms are the new master cryptographers, trained on petabytes of known signals to recognize the subtle fingerprints of natural phenomena. They learn the steady rhythm of a pulsar, the chaotic burst of a solar flare, and the distinctive chirp of merging black holes. With this knowledge, they can scan the endless cosmic static in real time, flagging the one signal in a million that breaks the established patterns. Projects like Breakthrough Listen employ sophisticated neural networks that act as intelligent filters, dramatically reducing the false alarms that once sent researchers on wild goose chases. This allows human scientists to focus their precious attention on the most promising and puzzling anomalies. Dr. Cherry NG and her colleagues are pushing this even further. They are teaching AI to model how a signal twists and bends as it travels through the turbulent soup of the interstellar medium. By understanding this journey, the AI can work backwards, sharpening the blurry origins of a fast radio burst to pinpoint its home galaxy with astonishing precision. This is not just about finding signals faster, it is about understanding them more deeply. The next frontier involves generative AI, which could simulate hypothetical alien languages or message structures. By creating millions of variations of potential communication based on universal mathematical and physical principles, we could test our decoding strategies against these synthetic messages, training our systems to recognize intelligence in forms we have not yet conceived. But this powerful tool raises profound ethical questions. As we outsource the first layer of cosmic interpretation to machines, what might we miss? An AI is trained on what we already know. Could it dismiss a truly alien signal because it does not fit any known category? The very act of filtering requires bias, and we must ensure our algorithms are built not to find what we expect, but to celebrate the truly unexpected. The great promise of AI is not to replace human curiosity, but to amplify it, guiding our attention to the whispers in the data that hold the greatest potential to change everything. Every journey through the cosmos leaves a mark on the message. A signal racing toward Earth for billions of years does not travel through a perfect vacuum. It must navigate a turbulent sea of ionized gas, clouds of cosmic dust, and tangled magnetic fields. This interstellar medium acts like a colossal, chaotic lens, subtly twisting and reshaping the signal until it is barely recognizable from its original form. A sharp, coherent radio pulse emitted from a distant galaxy can arrive at our telescopes as a stretched-out, scattered, and flickering echo. Think of a brilliant beam of white light passing through a prism, fanning out into a rainbow of colors. The interstellar medium does something similar to radio waves, a phenomenon known as dispersion. Higher frequencies of a radio burst outpace the lower ones, forcing astronomers to essentially reverse this cosmic smear to reconstruct the signal's true, sharp profile. This dispersion is not just a problem to solve, it is a treasure trove of information. By measuring the precise amount of this frequency spread, what scientists call the dispersion measure, they can calculate the total number of electrons the signal encountered on its epic journey. A fast radio burst with a high dispersion measure has traveled through a tremendous amount of material, allowing us to literally weigh the invisible stuff between galaxies. Another key effect is scintillation, the radio equivalent of a star's twinkle. Just as our atmosphere makes starlight shimmer, the turbulent plasma of the interstellar medium causes a radio signal's intensity to fluctuate, sometimes amplifying it, sometimes dimming it to near invisibility. Pioneering work by astrophysicists like Dr. James Cordes uses these distortions as a powerful diagnostic tool. By studying how a pulsar signal scintillates, they can map the invisible clouds of ionized gas that drift between the stars, charting the galaxy's hidden anatomy. So how do we clean a signal buried in cosmic noise? The process is a meticulous digital archaeology. Sophisticated algorithms are fed the raw, messy data. They know the mathematical fingerprints of dispersion and scintillation, and they work backwards, applying corrective filters to remove these interstellar effects. It is a painstaking effort to peel back the layers of a signal's long journey, to hear the original whisper as it was sent. This faithful decoding is the ultimate test of our cosmic listening skills. Can we be sure we are hearing the true voice of the universe? and not just the echo of its chaotic halls. A confirmed signal from an intelligent civilization would shatter our cosmic isolation in an instant. The ethical dilemma of how to respond is not a distant science fiction scenario, but a pressing global question with protocols already in place. If our telescopes ever capture a pattern that is unmistakably artificial, a specific set of international guidelines developed by groups like the SETI Post-Detection Hub would swing into action. Led by researchers like Dr. John Elliott, this framework dictates a meticulous process. The first and most critical step is verification. Scientists across the globe would independently confirm the signal's extraterrestrial origin, ruling out any human-made source or natural phenomenon. Only after this rigorous validation would the information be disclosed to the public. The manner of that disclosure is itself a profound ethical consideration. How do you tell the world that we are no longer alone? The goal is to avoid panic and misinformation, ensuring the news is shared calmly, accurately, and through official international channels. This careful, unified approach is vital because the societal impact would be unprecedented, reshaping philosophy, religion, and our very identity as a species. The next, even more contentious step is the question of a reply. Should we answer? The risks are the subject of intense debate. Some, echoing Stephen Hawking's caution, warn that broadcasting our location could invite a potentially hostile civilization, drawing a comparison to the disastrous consequences for less technologically advanced cultures in human history. Others argue that a society capable of interstellar communication would necessarily have moved beyond aggression, and that refusing to answer would be a failure of cosmic curiosity. The legal foundation for this exists in the Outer Space Treaty of 1967, which establishes that space is the province of all humankind, but it lacks specific rules for communication. This legal gray area underscores the need for new, robust ethical frameworks. Any decision to transmit a response cannot be made by a single nation or corporation. It must emerge from a global conversation involving scientists, ethicists, political leaders, and the public. What principles should guide our first interstellar conversation? Do we lead with our knowledge of mathematics and physics, or do we share our art and music? Do we present an idealized version of humanity, or an honest portrait with all our flaws and triumphs? The ethics of cosmic communication ensure that the monumental act of decoding a message leads to responsible collective action, transforming a moment of discovery into a testament to our planetary maturity. A gravitational wave pattern that defies all known physics could be our first glimpse of a neighboring universe. Picture the faint ripple from a collision so colossal it warps the fabric of spacetime, but its frequency and amplitude follow rules that do not apply in our cosmos. This is not science fiction, it is a serious possibility at the farthest edge of theoretical physics, where the multiverse hypothesis lives. Physicists like Dr. Max Tegmark have structured this idea, proposing that our universe is just one page in an infinite cosmic library, each with its own unique set of physical laws. In one universe, gravity might be stronger; in another, the speed of light could be a mere crawl. The question is, how could a signal from one of these other realms ever reach us? The answer might lie in anomalies, tiny cracks in the foundation of our reality. The cosmic microwave background, that ancient echo of our own beginning, could hold the first clues. A strange, cold spot in its otherwise uniform glow, or an unusual pattern of polarization, might not be a random fluctuation. It could be the cosmic bruise from a long-ago collision with another universe, a bubble brushing against our own in the vast metacosmos. Similarly, detectors buried deep underground, hunting for dark matter, might record a particle event with impossible energy, a visitor that should not exist according to our standard model of physics. Perhaps it slipped through a temporary rift, a quantum tear between parallel worlds. Decoding such a signal would be the ultimate challenge. It would demand a physics beyond Einstein, a framework that can describe not just our universe, but the interactions between countless universes. Finding proof of the multiverse would not just add new chapters to our science books, it would fundamentally rewrite our story of existence, transforming everything we know about reality from a single, solitary narrative into one of infinite, simultaneous possibilities. Are we listening for echoes from the void, or are we overhearing whispers from the room next door? A new era of cosmic listening is about to begin, one that will transform our faint whispers into a roaring chorus. The next generation of observatories, both on the ground and in space, are being built not just to see further, but to hear more clearly than ever before. The Square Kilometre Array, or SKA, will be the most sensitive radio telescope in history. Its thousands of antennas, spread across South Africa and Australia, will function as a single, colossal ear able to map the sky with a detail we can barely conceive. It will be so sensitive it could detect an airport radar on a planet dozens of light years away, allowing it to sift through the cosmic static for the faintest technosignatures. But its power goes far beyond the search for intelligence. The SKA will peer back to the cosmic dawn, listening for the faint radio hum from the formation of the very first stars and galaxies, a signal that has been traveling for over 13 billion years. Dr. Sarah Burke-Spoleyor highlights that this immense sensitivity is key to solving transient mysteries. It could capture thousands of fast radio bursts, mapping their origins with such precision that we might finally pinpoint the exact cosmic engines, be they magnetars or something even more exotic, that create these brilliant flashes. This is not just a bigger telescope. It is a wider net cast into the cosmic ocean, designed to catch the small, strange fish we never even knew were there. In space, the James Webb Space Telescope acts as a complementary eye to our new radio ears. While Webb sees in infrared light, piercing through cosmic dust to study the atmospheres of exoplanets, its data combined with SKA's radio observations creates a multi-messenger profile of distant worlds. They could work in tandem, with one detecting a potential technosignature and the other analyzing the chemical composition of that world's atmosphere for signs of industry or life. The next leap in listening will also occur in a completely different spectrum, the realm of spacetime itself. The Laser Interferometer Space Antenna, or LISA, is a planned gravitational wave observatory that will float in space. Free from the seismic noise of Earth, its 3 spacecraft, flying in a perfect triangle millions of kilometers apart, will detect low-frequency ripples that are completely invisible to ground-based detectors. LISA will hear the gentle, universe-spanning hum of millions of pairs of supermassive black holes dancing in the hearts of galaxies. It could detect the ripples from the very first black holes, and even hear the gravitational waves produced in the instant after the Big Bang. How will these tools tackle the universe's deepest mysteries? By providing a constant, high-definition stream of data, they will allow us to weigh dark energy directly by observing how it has influenced the large-scale structure of the universe over billions of years. They could reveal if fast radio bursts are indeed the signature of cosmic strings or other exotic phenomena predicted by theoretical physics. The next decade promises to turn our isolated whispers into a coherent conversation, a golden age where we do not just find signals, but finally begin to understand their stories. The moment a confirmed alien message flashes across our screens, our world would transform in an instant. This would not be a quiet scientific discovery, but a global event reshaping every facet of human culture. History offers us glimpses of how we might react. The appearance of Halley's Comet has been interpreted for centuries as an omen, a celestial herald of change. The infamous War of the Worlds radio broadcast in 1938, though a fictional drama, demonstrated our capacity for collective anxiety, as many listeners believed a real Martian invasion was underway. A genuine message from the stars would trigger a media storm of unimaginable scale, a 24/7 cycle of speculation, analysis, and fear. Scientific euphoria would be palpable, a triumphant validation of centuries of curiosity. But this excitement would exist alongside deep uncertainty. Religious institutions would grapple with the theological implications, reinterpreting scriptures to encompass a creation far wider than ever conceived. Would this discovery be seen as an affirmation of a divine creator or a challenge to earthly dogma? Dr. Catherine Denning, an anthropologist who studies the societal aspects of astrobiology, emphasizes that our reaction would hinge entirely on the message's content. A complex stream of prime numbers or a simple greeting might inspire global unity, a sense of joining a cosmic community. A signal containing schematics or a warning, however, could just as easily fracture international cooperation, sparking geopolitical strife over how to proceed. Our creative expression would be forever altered. Art, music, and literature would explode with new themes, moving beyond tales of invasion to explore profound questions of connection and identity. Philosophy would undergo its greatest shift since Copernicus moved us from the center of the universe. We would be forced to see ourselves not as a solitary miracle, but as one voice in a chorus of cosmic life. This psychological dimension is not a side effect of decoding. It is the very heart of the challenge. Preparing for this possibility is not about building a bigger telescope, but about fostering a global conversation. How do we cultivate the wisdom, the patience, and the unity we would need to not just hear a message, but to understand its place in our shared future? A dramatic signal from the stars makes for a compelling movie plot, but the everyday reality of cosmic listening is far more gradual and collaborative. Popular films like Contact and Arrival present a captivating vision of instant decoding, where a complex message is swiftly understood by a lone genius. The truth is a global effort involving thousands of scientists, years of painstaking data analysis, and a rigorous process of elimination that usually ends with a natural, if spectacular, explanation. The late astronomer Carl Sagan was a master at navigating this terrain, championing the boundless possibilities of the cosmos while firmly anchoring his work in the scientific method. He reminded us that extraordinary claims require extraordinary evidence, a principle that guides every analysis of a potential signal. This disciplined approach is crucial because the universe is filled with natural phenomena that can mimic artificiality. The perfectly timed pulses of a pulsar were initially mistaken for a deliberate beacon. The complex structures within some fast radio bursts can appear strangely ordered. Our greatest challenge is not a lack of imagination, but the overwhelming creativity of nature itself. A common public misconception is that any signal we cannot immediately explain must be a sign of intelligence. This leads to a cycle of excitement and disappointment when the signal is later traced to a passing satellite, a terrestrial microwave oven, or a previously unknown type of stellar explosion. Another persistent myth is the idea that advanced civilizations are deliberately ignoring us, a notion that assumes both their awareness of our existence and a unified, indifferent intent. The reality is that space is vast, time is deep, and our own technological signature has only been detectable for a little over a century, a mere blink in cosmic terms. Fostering public understanding does not mean crushing wonder with cold facts. It means replacing the simplistic myth of the alien hello with the far more profound story of how we are learning to read the universe's own diary. This is a narrative of patient discovery, where each decoded signal, whether from a colliding black hole or a dying star, adds a new sentence to an epic story billions of years in the making. How do we share this grand, collaborative endeavor without losing the public's sense of excitement? The answer lies in inviting everyone to appreciate the mystery itself, not just the potential for a single, world-changing answer. By dispelling the myths, we clear the path for a more authentic and ultimately more rewarding relationship with the cosmos. Your own backyard could become a listening post for the cosmos. The search for cosmic signals is no longer confined to mountaintop observatories and giant satellite dishes. A global movement of amateur astronomers and citizen scientists is now joining the hunt, using accessible technology and their own innate curiosity to scan the heavens. This is a profoundly democratic endeavor, opening the search for cosmic messages to anyone with an interest and an internet connection. One of the most impactful ways to contribute is through distributed computing projects like SETI at home. This pioneering program allowed millions of people around the world to donate their home computers' unused processing power. While the project is now in hibernation, its model proved that a virtual supercomputer, built from countless personal machines, could sift through immense volumes of radio telescope data, searching for the subtle signature of an artificial signal that a single computer might miss. For those who want a more hands-on approach, platforms like Xenoverse host a variety of space-related citizen science projects. Here, volunteers can use their own eyes and brains to classify images and signal patterns. The human brain's exceptional pattern recognition skills are still often superior to algorithms at spotting oddities, the strange glitch or the unusual curve that might be the key to a new discovery. Experts like Dr. H. Paul Schuch, a founding figure in amateur SETI, have long championed this grassroots effort. He and others provide detailed guides for building affordable radio receivers and software-defined radios that can be paired with a modest satellite dish. With this basic setup, you can begin monitoring a specific patch of sky, logging data on radio frequency interference, and even searching for the steady pulse of a previously unknown pulsar. In fact, amateur astronomers have made legitimate discoveries, identifying new pulsars and noting anomalous transient events that later warranted professional investigation. Their contributions prove that you do not need a billion-dollar budget to advance our understanding of the universe, only a dedicated and curious mind. So what do you actually need to begin? A basic understanding of radio astronomy principles is a great start, along with some patience for troubleshooting technical equipment. A simple radio telescope kit, a computer for data analysis, and access to online communities where you can share findings and learn from others are the core tools. This public engagement does more than just expand the number of eyes on the sky. It weaves a global network of listeners, transforming the search for cosmic messages from an elite scientific pursuit into a shared human adventure, where the next great discovery could come from a rooftop antenna just down the street. This profound silence from the stars is not an empty void, but a message in its own right, one that forces us to confront our deepest questions about existence. The universe's apparent quiet speaks volumes about our place within it, asking us to consider whether we are a cosmic miracle or a cosmic accident. Imagine a reality where our planet is the sole bearer of consciousness, a single, fragile candle flame in an unimaginably vast and unconscious dark. Or perhaps the silence is a choice, a deliberate decision by advanced societies to remain hidden, observing us from a distance for reasons we cannot yet grasp. This line of thinking has led philosophers like Dr. Nick Bostrom to propose a sobering possibility known as the Great Filter. This is the idea that somewhere on the path between non-life and a galaxy-spanning civilization, there exists an evolutionary or technological barrier so difficult to overcome that it stops nearly everyone. The haunting question is whether this filter lies in our past, making us incomprehensibly rare, or in our future, waiting for us just ahead. Our continued silence could be the echo of countless civilizations that reached our stage of development only to flicker out. Yet there is another, more hopeful interpretation of the quiet. It may not be that the galaxy is empty, but that we are simply deaf to the true conversation. A society far more advanced than our own might have long ago moved beyond the crude technology of radio waves. Their communications could be woven into the quantum fabric of spacetime, using entangled particles for instantaneous links across light years. Or perhaps they have learned to communicate through extra dimensions, their messages passing through our reality like a whisper through a wall, completely undetectable to our current instruments. How do we search for a language we have no dictionary for? This cosmic silence, therefore, becomes the ultimate philosophical test. It challenges our anthropocentrism, our innate tendency to believe that others would think and communicate exactly as we do. The void invites us to interpret nothingness, to find meaning in the absence of a signal. It pushes our science to look for subtler clues, for the silent artifacts of technology rather than a shouted hello. In the end, the great quiet may be teaching us the most valuable lesson of all, that the universe does not owe us an answer, and that the search for meaning begins not with a message from the stars, but with a deeper understanding of ourselves. The universe often whispers its greatest secrets when we are listening for something else entirely. Serendipity has been a quiet partner in our quest to decode the cosmos, turning routine tasks into revolutionary discoveries. The story of the cosmic microwave background is a perfect example. Arno Penzias and Robert Wilson were not looking for the echo of creation. They were simply trying to eliminate a persistent hiss from a sensitive radio antenna, a nuisance they initially blamed on pigeon droppings. Their careful, frustrated efforts to clean the instrument led them not to a technical fault, but to the cooled remnant of the Big Bang itself. Dr. Robert Wilson's own reflections on the discovery are marked by a profound humility. He often noted that they were not cosmologists searching for the universe's origins. They were engineers trying to solve a practical problem, and their openness to the data led them to a truth far grander than they had sought. This pattern of accidental discovery repeats itself throughout history. The first pulsars were detected by Jocelyn Bell Burnell as strange, scruffy signals on a paper chart, anomalies that were initially dismissed as possible terrestrial interference before being recognized as the rhythmic pulses of spinning neutron stars. In both cases, it was not a targeted search that found the answer, but a prepared mind that recognized the significance of an unexpected result. This is the essence of scientific serendipity, the happy marriage of chance and a curious, analytical intellect. A researcher simply going through the motions might have discarded the anomalous data as noise, but a prepared mind asks why. Why is this signal here? Why does it not fit our expectations? This mindset is what transforms static into a message. As we design ever more powerful algorithms to sift the cosmic noise for specific patterns, we must consciously build in room for the unexpected. Our targeted searches for fast radio bursts or deliberate alien messages are vital, but they can create blind spots. What if the most important signal is one we are not even looking for, a pattern that does not match any of our predefined categories? Vast archives of telescope data already exist, filled with observations collected for other purposes. Hidden within those terabytes of information could be a signal waiting for a new perspective, a fresh pair of eyes, or a smarter algorithm to notice the one detail everyone else overlooked. The future of cosmic decoding depends on this balance, a dance between disciplined, targeted investigation and a childlike openness to sheer wonder. By embracing serendipity, we keep the cosmic conversation full of surprises, ensuring that our search for signals remains a journey of genuine discovery, not just a process of confirmation. Our journey through the cosmic symphony has reached its final movement, but the music plays on. We have listened to the faint ripples of gravitational waves and the explosive screams of gamma-ray bursts. We have considered the ghostly passage of neutrinos and the disciplined pulse of distant pulsars. Each signal, whether a natural physical process or a tantalizing hint of something more, is a vital piece in the grand puzzle of our existence. They are not just random noises, but structured stories written in the universal language of physics, waiting for us to learn the grammar. This is not the end of our listening, but a new beginning. With every advance in artificial intelligence, with every new telescope that stretches our senses, we refine our ability to interpret these cosmic whispers. The silent question posed by the Fermi Paradox, the ethical labyrinth of a potential reply, the philosophical weight of the great filter, these are not barriers but signposts on a much longer road. They compel us to look deeper and to think more broadly about our place in the cosmos. The most profound realization is that the act of listening itself has transformed us. We are no longer passive inhabitants of a small world, but active participants in a cosmic conversation, learning to read a diary that spans billions of years. Our tools will grow sharper, our algorithms wiser, and our collective understanding will continue to evolve. What message would you dare to send into that vast stillness, a greeting from one conscious spark to another? Share your thoughts below and join us as we keep exploring the great mysteries of space. The universe has been speaking for eons, and our great work is simply to learn how to hear.